Somewhere beyond the sweep of our immediate solar neighborhood, the Milky Way reveals itself not as a silent arc of stars across the night sky, but as a sprawling system with intricate architecture and hidden depths, 100,000 light-years wide. This galaxy is a continent of stars suspended in a void, its center veiled behind curtains of dust in the direction of the constellation Sagittarius. Light itself, the fastest known messenger in the universe, would take a full 100 millennia to cross its breadth. And yet, in all that vastness, our own sun is just a minor player, situated about 30,000 light-years from the galactic center, orbiting it with measured grace every 200 million years. The Milky Way's visible body is a disk, but this disk is more than a flattened spiral of stars. It is a living, rotating structure, dense with interstellar gas and flecks of microscopic dust that veil and reveal depending on the observer's vantage point. Embedded in this disk is over half the galaxy's observable mass stars of varying ages and chemistries, gas clouds primed for stellar birth, and fragments of dust forged from long-dead stars. Only about 1% of this matter consists of dust, yet that sliver plays a disproportionate role in shaping what we can and cannot see. These dust grains, smaller than a micron, are the ashes of stellar cycles, riding the galactic winds and gathering in the cold nurseries where new stars begin to shine. The Sun, a population one star born from gas already seeded with heavy elements, is one of many in this enriched region of the disk. Unlike its older cousins in the halo, it formed from gas that had witnessed previous generations of stellar death and rebirth. These earlier stars forged elements heavier than helium-carbon, oxygen, silicon, iron, and dispersed them into space. Over time, these materials coalesced into dust grains, then into meteoroids, and eventually into planets. It's from this lineage that Earth itself was born, a world possible only in a galaxy old enough to recycle itself. Circling this luminous disk like a ghostly shroud is the galactic halo, an enormous, faintly populated region stretching nearly 200,000 light-years across. It is not symmetrical or vibrant like the disk. Instead, it is sparse and ancient, a graveyard of primordial stars. The halo does not rotate in concert with the disk. Its stars drift in elliptical orbits, indifferent to the ordered dance below. These are population 2 stars old, metal poor, relics from a time before galaxies had matured. Many are gathered into globular clusters, each a self-contained sphere of hundreds of thousands of stars, all born together over 8 to 15 billion years ago. In these stars, the periodic table ends early. With virtually no heavy elements, their chemistry would not permit the formation of complex planetary systems. In a very real sense, they are orphans of cosmic evolution formed too early, from too little, in an era before stars could build the ingredients for worlds. If intelligent life is to exist, it would almost certainly favor the newer stars, the ones born from richer materials, in denser and more dynamic parts of the galaxy. Between the disk and the halo lies a transitional zone, the nuclear bulge. This central sphere is a gravitational furnace of stellar activity, where population 1 and 2 stars intermingle. The region is so crowded that stars lie hundreds of times closer to each other than in our corner of the galaxy. Dense gas flows here in eddies and spirals, and embedded within this chaos, perhaps hidden beneath the glare of surrounding matter, are the suspected giants, supermassive black holes whose gravitational appetites drive the complex energy dynamics of the core. Star clusters offer a way to measure the distances that separate these structures. Open clusters, loosely bound groups of young stars dot the disk and often cling to their birth clouds for a few million years. The Pleiades and Hyades clusters are close enough for astronomers to calculate their distances through parallax and Doppler-based methods. Globular clusters, on the other hand, are scattered mostly in the halo and nuclear bulge, with precise alignments that allow scientists to calibrate distance scales using brightness and temperature. The Hyades cluster plays a pivotal role in this cosmic cartography. It acts as a yardstick for the galaxy and, by extension, the universe. Through techniques like the moving cluster method and main sequence fitting, its measured distance enables astronomers to leapfrog across space using pulsating Cepheid stars as lighthouses to estimate the distances of remote galaxies. Dust, however, complicates everything. Even the clearest cosmic window is rarely truly transparent. The interstellar medium is thick with particles that obscure, absorb, and scatter starlight. Like fog dimming the view across a field, these clouds can reduce a star's brightness to a fraction of its intrinsic glow. Every 3,000 light-years through the disk, the intensity of visible starlight is halved. Beyond 6,000 light-years, the dimming can make stars appear just 1/4 as bright as they would otherwise be, an effect that masks the galaxy's heart from view. Yet this shroud is selectively permeable. Long wavelength light in the infrared and radio ranges pierces through the dust, where optical telescopes see only a void. Instruments tuned to these wavelengths reveal a roiling, star-strewn core. This central bulge, extending 10,000 light-years from the nucleus, is not a featureless void but a labyrinth of stellar birth and death, of collapsing clouds and radiating gas. Multiple sources of strong radiation suggest something formidable lies hidden, perhaps one or more supermassive black holes, concealed not by design, but by dust and distance. As segment 1 fades, it leaves behind a vision of the Milky Way not as a static map of star positions, but as a dynamic arena of birth and memory, structure and entropy. From the ordered orbits of population 1 stars to the drifting remnants in the halo, this first layer of our galactic understanding sets the stage for deeper questions about cosmic structure, stellar evolution, and the forces that shape everything from black holes to planetary systems. Turn your gaze outward past the boundary of our galactic halo, beyond the reach of our sun's gravitational leash, and the solitary glow of our Milky Way gives way to a spectacle far grander, a universe laced with galaxies. What once appeared to the human eye as faint, cloudy smudges on telescope plates have been resolved into entire star cities. Each galaxy, in motion and in flux, spins its own narrative of birth, transformation, and decay, set within a vast web of structure that challenges our every cosmological model. These galaxies are not scattered at random, like raindrops on a spider web. They stretch across the cosmos in filamentary threads and clustered knots. Some are faint, irregular sparks barely distinguishable from globular clusters. Others, like Andromeda or M87, are monumental, their diameters surpassing 500,000 light-years. Most galaxies fall into recognizable shapes: elliptical, spiral, barred spiral, each category a frozen frame from the universe's dynamic evolution. Elliptical galaxies are the most common, making up over 60% of all known galaxies. Their forms are ovoid, smooth, and largely featureless, from the near-spherical E0s to the more elongated E17s. These systems are the ancient vaults of the universe. They lack spiral arms, possess little gas or dust, and contain mainly population 2 stars, ancient, low-metal stars born when the universe itself was still cooling into complexity. Some are mere dwarfs, only marginally larger than star clusters. Others, like the supergiant M87, are monstrous in scale, containing hundreds of billions of stars and harboring colossal black holes in their cores. These elliptical giants often dominate the gravitational centers of galaxy clusters, growing fat on mergers and cosmic cannibalism. In contrast, spiral galaxies like our own wear their age more flamboyantly, with bright, swirling arms wrapping around dense nuclear bulges. They offer a vivid tableau of ongoing stellar life. Their disks are rich in gas and dust, ideal conditions for star formation, and their arms sparkle with the blue-white intensity of young, short-lived stars. These spiral arms are not static structures, but moving density waves, regions where interstellar gas is compressed just enough to trigger gravitational collapse. Newborn stars blaze briefly before fading, leaving behind clusters and remnants that slowly drift away. The spiral arms' longevity presents a paradox. If stars and gas rotated within them as solid features, they would wind tighter and tighter over time, contradicting the loose pattern seen in even the oldest galaxies. This winding problem found its solution in Bertil Lindblad's density wave theory. The arms are not collections of fixed stars, but are more like traffic jams, ripples in space density through which stars and gas pass. This ripple triggers waves of star formation without requiring a rigid structure. The luminous arms are ephemeral, lit by stars that will soon burn out or drift away. but the underlying wave pattern persists, like music played across cosmic time. Galaxies aren't static islands. They belong to groups, clusters, and superclusters. Gravitational associations on scales so immense they defy everyday experience. Our Milky Way is a member of the local group, a modest, irregular cluster of around 20 major galaxies. Its most prominent neighbors, the Andromeda Galaxy and the Triangulum Galaxy, are spirals as well, and the gravitational interplay among them is already reshaping the future. Billions of years from now, Andromeda and the Milky Way will collide and coalesce, forming an elliptical galaxy far larger than either progenitor. Beyond the local group lies the Virgo cluster, a clumpy, irregular swarm of galaxies located about 70 million light-years away. Rich clusters like Virgo contain thousands of galaxies, from delicate spirals to hulking ellipticals. They lack the symmetry of globular star clusters, but exert influence across cosmic distances. Even more massive are the so-called regular clusters, like the Coma cluster, which stretch 10 million light-years in diameter and teem with thousands of galaxies bound together by gravity and perhaps even dark matter. These galaxy clusters are not merely gatherings of stars. They are violent arenas. As galaxies plunge through their environments at thousands of kilometers per second, they interact with streams of intergalactic gas. This high-speed motion through dense plasma can strip galaxies of their own gas, halting star formation and transforming them from active spirals into passive lenticulars. These S0 galaxies, once rich with life, now resemble swept-clean versions of spirals disks without the glow, arms without the pulse. The broader architecture of the universe begins to emerge only when we step even further back. Galaxy clusters themselves group into superclusters, forming a foam-like structure, a vast web where filaments of galaxies are separated by voids spanning hundreds of millions of light-years. Our local group resides within the Laniakea supercluster, which is centered near the Virgo cluster. The structure is gravitationally complex, shaped not only by the visible matter we observe, but also by a scaffolding of dark matter that tethers galaxies into these immense patterns. In trying to understand the variety of galaxies, astronomers have long sought a taxonomy. The most iconic is Edwin Hubble's tuning fork diagram. On one side lie elliptical galaxies, from nearly round E0s to elongated E7s. At the junction are S0 galaxies disc-shaped but gas-poor. From there, the diagram forks into two branches, normal spirals and barred spirals, categorized by the size of their central bulges and the tightness of their arms. Though it was once thought that this diagram reflected evolutionary paths, with galaxies morphing from left to right, or vice versa, modern consensus suggests otherwise. A galaxy's form may be more a matter of birth conditions, density, rotation, and local environment than any smooth transformation over time. But not all galaxies fit the mold. A significant fraction, around 10%, are irregular, defying neat classification. Some are the victims of tidal interactions or galactic collisions. Others are simply primordial systems, never having enough mass to settle into an ordered shape. The small and large Magellanic Clouds, visible in the southern hemisphere's skies, are examples of such irregular galaxies nearby neighbors with chaotic structures shaped by gravitational wrestling with the Milky Way. Here, at the boundary between order and chaos, the story of galaxies becomes one of tension between environment and destiny. Some galaxies are born quiet and remain so, coasting through cosmic time with little disruption. Others are pulled into violent mergers, flung across clusters, or devoured by their larger companions. Yet through all these upheavals, they follow unseen laws, gravity, thermodynamics, and the slow whisper of dark energy stretching the universe like a breathing lung. As we look deeper into space, we also look further into the past. The light from a galaxy 10 billion light-years away left its source when the universe was a fraction of its current age. In that light, we read stories not just of distant structures, but of our own origins. Every distant galaxy is a time capsule, preserving the physics and conditions of an earlier epoch. They hint at a time when galaxies were smaller, more chaotic, and far more prone to rapid star formation. As this segment closes, We find ourselves surrounded by patterns writ large across space, spiral arms, and elliptical swarms, dwarf irregulars and giant clusters all dancing to a rhythm we are just beginning to hear. The universe, once thought to be a scattering of stars, now reveals itself as a carefully choreographed network of galaxies, each a glowing node in a cosmic tapestry. There was a time long before Earth had oceans, long before the sun ignited when galaxies themselves did not yet exist. No elegant spirals or luminous bulges, no clusters or superclusters to carve patterns across the sky. Instead, there was only gas, a uniform expanse of hydrogen and helium, cooling in the aftermath of the Big Bang, expanding like breath into cold air. But even this early universe, seemingly simple, bore within it tiny imperfections, minute differences in density that would become the seeds of all structure. These primordial variations, less than 1 part in 100,000, were not errors but blueprints. Over eons, gravity acted on them, nudging denser regions to grow denser still. As the universe expanded, the average density of matter decreased, but those slightly over-dense regions' protuberances in an otherwise smooth fabric resisted the thinning. Their relative density increased until, at some critical threshold, they began to collapse. From these gentle perturbations, proto-galaxies were born. A proto-galaxy was not a single object, but a region often hundreds of thousands of light-years across where gas slowed, halted its outward drift, and began to fall inward. This gas, still composed mostly of hydrogen and helium forged in the Big Bang, was cool and diffuse. Its fate depended on 3 crucial factors: its mass, its initial rotation, and its internal irregularities. In regions with higher mass, gravity pulled more strongly. Where there was rotation, centrifugal force pushed back. And in areas of internal clumpiness, collapse occurred unevenly, giving rise to the earliest generation of stars. These first stars, population 2 stars, were born in the densest central regions of proto-galaxies, lacking heavy elements. They were composed almost entirely of primordial gas. Many were massive, burning their nuclear fuel rapidly and dying in violent supernova explosions. In their deaths, they seeded their surroundings with heavier elements: carbon, oxygen, iron, the raw materials from which later stars, planets, and eventually life would form. This chemical alchemy, repeated across millions of such first-generation stars, enriched the collapsing gas clouds with each cycle of death and birth. As the proto-galaxy collapsed further, a striking phenomenon occurred. The stars, once formed, ceased to participate in the general infall. Each star followed an orbit around the growing center, but unlike gas, it could not dissipate energy through collisions or radiation. It remained suspended in motion, while the gas continued to sink. Over hundreds of millions of years, this differential behavior sculpted the emerging galaxy's structure. The early spherical swarm of stars, the halo, remained a fossil record of this initial collapse, while the infalling gas eventually settled into a rotating disk. Here lies a subtle insight: the stars in the halo, the gas in the disk, and the shape of the galaxy are not independent phenomena. They are chapters in a single gravitational history, unfolding in time. A galaxy's form, spiral or elliptical, reflects the balance of forces at play during its formation. In cases where rotation dominated, gas was able to flatten into a disk, forming spirals rich in ongoing starbirth. In galaxies where collapse outpaced spin, the result was more spherical, a structure that consumed its gas rapidly, leaving behind a population of aging stars and little fuel for the future. Yet the narrative does not stop with formation. These early galaxies, already differentiated in shape and content, interacted, merged, and evolved. Some spirals collided and formed ellipticals. Some dwarf galaxies were cannibalized by larger hosts. Some retained their integrity for billions of years, like cosmic islands drifting in a sea of expansion. But at the heart of all these changes lay one common force: gravity, ever at work sculpting structure from chaos. Consider a proto-galactic cloud with moderate rotation. As its outer gas collapses inward, the increasing spin creates a barrier. Centrifugal force flattens the flow into a disk. The central region, less affected by this force, becomes a halo. Here, population 2 stars light up first, followed by generations of increasingly metal-rich stars in the disk. Magnetic fields, turbulence, and stellar winds complicate this picture, impeding or delaying star formation. But over time, a majestic spiral emerges, its arms cradling newborn stars, its halo preserving echoes of a forgotten past. Now imagine another scenario, the same cloud, but with higher density and less spin. Collapse occurs more quickly and more uniformly. The gas doesn't have time to settle into a disk. Instead, it feeds an orgy of rapid star formation. With little rotation to resist infall, the gas is consumed before it can spread out. The result, an elliptical galaxy, dense, old, and quiet. Star formation ends early, and the structure remains largely unchanged for billions of years. This dichotomy, disk versus spheroid, spiral versus elliptical, underlies much of modern galaxy classification, but nature, as always, permits exceptions. Intermediate forms emerge. Galaxies with moderate rotation but clumpy collapse may form lenticular shapes. Those with strong initial density variations may fragment into multiple components, and some, battered by collisions or gravitational tides, bear little resemblance to either category, becoming irregular or peculiar in appearance. The process of galaxy formation also invites a broader philosophical contemplation. These structures, vast beyond comprehension, arise not from divine intervention or miraculous design, but from the slow, inexorable unfolding of simple laws. The same equations that govern falling apples and orbiting moons shape the birth of galaxies. Yet from these laws, an astonishing complexity emerges: order, symmetry, beauty. In contemplating the origin of galaxies, we are drawn into a meditation on emergence, how simplicity breeds structure, how chaos gives rise to form. And what of time to us? Galaxies seem eternal, their shapes unchanging across the millennia. But this is an illusion born of scale. Galaxies live, evolve, and die. They merge, shift, and bleed their energies into space. Some lose their gas to intergalactic winds, others collapse into active nuclei. A galaxy that once blazed with newborn stars may one day become a ghost, its brilliance faded, its arms smudged into obscurity. Seen in this light, galaxies become more than astrophysical phenomena. They are timelines, each one recording a different version of cosmic history. Some tell of quiet births and long, graceful evolutions. Others are chronicles of violence, of mergers, collisions, and sudden transformations. And embedded within each is the memory of conditions from a time when the universe was young, denser, and hotter. The current distribution of galaxy types, then, is not arbitrary. It reflects the timing of their formation, the initial conditions of the expanding universe, and the complex choreography of matter under gravity. Fragmentation and aggregation, these two principles, once thought opposed, now appear as partners in a universal dance. From tiny fluctuations in density came the building blocks of structure. From collapsing globes came stars. From the clustering of galaxies came superclusters. And from them, the vast, luminous web that defines our cosmic environment. The very idea that a region with only one hydrogen atom per cubic centimeter, a vacuum by terrestrial standards, could give rise to such richness speaks to the astonishing scale of cosmic processes. What seems empty to us is, on galactic scales, a sea of possibility. What begins as a whisper of imbalance becomes, through time and gravity, a voice shouting across the ages in the form of stars, clusters, and galaxies. In the next arc of our story, we will dive inward again, not into space, but into energy. We will examine what happens when gravity, unopposed, ignites not just stars, but entire galactic cores, turning galaxies into lighthouses visible across the universe, and revealing the monstrous hearts that dwell within. Somewhere in the depths of a galaxy, not in the quiet outskirts where stars drift serenely, but in the violent central furnace where matter crushes into itself, a singular hunger awakens. This is not a star, nor even a cluster of stars. It is a presence invisible, insatiable, and capable of swallowing light itself. At the core of many galaxies, including our own, lies a black hole, not just any black hole, but a supermassive one, containing millions or even billions of solar masses compressed into a volume scarcely larger than our solar system. To encounter such an entity is to brush against the limits of what physics can describe. A black hole is not a thing so much as a region of altered reality, where gravity warps space and time to extremes. But it is not the black hole alone that makes a galaxy's center luminous. Paradoxically, it is what surrounds it, gas spiraling inward, forming a blazing accretion disk heated to millions of degrees that transforms these invisible monsters into some of the brightest objects in the universe. These blazing hearts are what we now call active galactic nuclei, and when they flare to their fullest intensity, we see them as quasars, quasi-stellar radio sources. Though not all are loud in radio, from billions of light years away, they send us signals, not voices, but pulses of energy so vast that for a time, they outshine entire galaxies. They vary in brightness from week to week, sometimes day to day, which means their engines must be astonishingly compact, smaller than the distance from the Sun to Pluto, yet releasing energy equivalent to hundreds of millions of suns. The analogy is often made between quasars and cosmic lighthouses, but that metaphor understates the violence. These are furnaces of annihilation, converting matter into energy with efficiencies unmatched by any known process short of total nuclear conversion. As gas falls into a black hole's accretion disk, it accelerates, collides, compresses, and heats. Magnetic fields twist and snap. Particles reach energies that dwarf anything our machines can achieve. The process is chaotic, yet strangely efficient. Perhaps 10% of the infalling matter's mass is transformed into radiant energy, released across the electromagnetic spectrum. And not all of that energy radiates passively. Some of it is funneled into jets, collimated beams of plasma that shoot from the poles of the accretion disk at near light speeds, stretching hundreds of thousands of light years into intergalactic space. These jets carve tunnels through the surrounding medium, lighting up radio lobes that balloon like smoke rings around the host galaxy. From Earth, we see them as two lobes of radio emission straddling a galaxy too distant to resolve, like twin searchlights from some forgotten war. The mechanisms behind these jets are still not fully understood. Some theories invoke magnetohydrodynamics, the same physics that governs sunspots and solar flares, magnified a billionfold. Others suggest that the rotation of the black hole itself, the so-called Kerr metric, twists spacetime, dragging magnetic field lines and launching particles outward. Whatever the cause, the result is spectacular radiation bursts that can last millions of years, shaping the galaxy's evolution and influencing its neighbors. Yet quasars do not burn forever. They flare, shine, and fade. When their fuel runs low, when the surrounding gas has been consumed, blown away by radiation pressure, or ejected by gravitational feedback, they fall silent. The accretion disk dissipates. The jets vanish. The black hole remains, quiet and cold, unless fresh gas stirs it awake once more. The transient nature of quasars suggests that most, perhaps all, large galaxies host supermassive black holes at their cores, and that those black holes go through active phases when conditions permit. In spiral galaxies like our own, the central black hole is often dormant or only modestly active. But in ellipticals, particularly those in crowded galactic clusters, activity can surge. This raises provocative questions. What governs a black hole's feeding schedule? What wakes it? What puts it to sleep? The relationship between a galaxy and its central black hole is not one-directional. While it was once thought that black holes were mere byproducts of galactic evolution, evidence now suggests a deeper interdependence. The mass of a galaxy's bulge correlates tightly with the mass of its central black hole, implying that they co-evolve. Radiation and outflows from active nuclei can regulate star formation by heating or expelling gas. Feedback, in this context, is not a metaphor. It is a literal, energetic coupling between a galaxy's heart and its extended structure. To probe this relationship further is to confront one of the most fascinating frontiers in modern cosmology. Why do galaxies with larger bulges have larger black holes? Does the growth of one limit the other? And what mechanisms ensure this cosmic tuning? Across billions of years and light years, the balance suggests a form of regulation, self-limiting growth, perhaps driven by the same physics that governs planetary atmospheres or ecological systems. In exploring these dynamics, we glimpse a universe where matter behaves like memory. Gas clouds remember the energy they've absorbed. Stars remember the metals forged by earlier generations. Black holes remember every photon they've consumed, storing mass without revealing it. And galaxies, as structures, remember their origins through the quiet echoes of their most violent epochs. But the significance of quasars, AGN, and black holes extends beyond astrophysics. They challenge our philosophical frameworks. Here are entities that cannot be seen directly, yet whose influence is undeniable. They remind us that reality is not limited to the visible, that the most powerful forces in nature are often cloaked in shadow. They are monuments to the limits of our perception and invitations to stretch those limits further. Imagine standing on a planet orbiting a star that once belonged to a quasar-hosting galaxy. In its sky, there might have been a time when night was not dark, when the galactic core blazed like a second sun. The spectacle would have lasted for epochs, longer than civilizations. And then, as quietly as it began, the light would fade. The black hole would remain, silent and unremarkable, as though the fire had never been. These cosmic flickers remind us of transience at scales we rarely consider. They are not just lights in the sky, but chapters in a story of becoming birth, hunger, radiance, decline. They are galactic myths, written in X-rays and radio waves, whispered across billions of years. In the next and final arc of our journey, we will follow these whispers outward beyond galaxies and clusters, into the web of the cosmos itself. We will trace the structures that galaxies form, and explore the frontier where cosmology meets origin, how the universe gave rise not just to stars and black holes, but to the framework of space-time we call reality. The sky above, so apparently empty, is a structure of astonishing complexity. Through the lens of modern astronomy, the cosmos reveals itself not as a scattering of isolated galaxies drifting in random solitude, but as an immense, interconnected web of filigree of matter that stretches across the observable universe, shaped by forces rooted in the earliest instants of time. Clusters of galaxies, each containing thousands of constituent systems, gather into even larger conglomerates, superclusters, bound loosely by gravity and connected by vast filaments of gas and dark matter. These filaments span hundreds of millions of light years, woven together like the threads of an invisible lattice. Between them are cosmic voids, enormous regions of near-nothingness, where only a few galaxies reside. It is this cosmic web that frames the large-scale structure of the universe. Our own local group, a modest collection of about 30 galaxies including the Milky Way and Andromeda, belongs to the Virgo supercluster, which in turn is part of a still grander structure known as Laniakea, a name that means immeasurable heaven in Hawaiian. But these designations, however poetic, fail to convey the scale. The Virgo supercluster alone spans over 100 million light-years, yet even it is just one among many. As we peer farther into space, we look deeper into time. Light from the most distant galaxies began its journey billions of years ago, when the universe was young and galaxies were more primitive, compact, and chaotically formed. These early structures were shaped by gravity acting on minuscule ripples in the density of matter fluctuations born during the first fractions of a second after the Big Bang. It is within these fluctuations that the seeds of all structure were sown. To understand how galaxies emerged from this primordial soup is to confront a sequence of delicate thresholds. When the universe was just a few 100,000 years old, it cooled enough for protons and electrons to combine into hydrogen atoms. This recombination rendered the universe transparent, allowing light to move freely. We observe this light today as the cosmic microwave background, a faint, uniform glow that fills the sky in every direction. But that calm was deceptive. Underneath the uniformity were those subtle variations, places where matter was slightly more dense. Over billions of years, gravity amplified those imperfections. Matter clumped, gas cooled, and stars ignited. Protogalaxies formed, collapsed, and merged. In some regions, immense concentrations of matter became the cradles of galaxy clusters. In others, matter flowed outward, leaving voids behind. The universe sculpted itself through a dance of attraction and expansion. The competing influences of gravity and dark energy define this process. Gravity pulls matter together, forging structure. Dark energy, the mysterious force accelerating the expansion of space, acts in opposition, driving galaxies apart. Their interplay has defined the universe's evolution since its earliest epoch. At present, dark energy dominates. Galaxies not bound in clusters are receding from one another at ever-increasing speeds, their light redshifted into invisibility. This cosmic acceleration means that some galaxies we now observe will, in time, vanish from view altogether. Beyond a certain horizon, the so-called cosmic event horizon light emitted today will never reach us. It is not that the galaxies are moving faster than light, but that the space between us and them is stretching too quickly. To observe the universe, then, is also to witness a kind of slow disappearance, a graceful, irreversible fading. And so the cosmos becomes a narrative about presence and absence, about what can be seen and what is forever out of reach. It is a theater of becoming and forgetting. Each star that dies, each galaxy that recedes, each quasar that dims, adds to the silent memory inscribed across space-time. In this context, even the vastest structures become ephemeral. Superclusters are not gravitationally bound holes over unimaginable time spans. They too will dissolve. The cosmic web will stretch into filamentary remnants. Clusters will become isolated archipelagos. Eventually, star formation will cease. The brightest lights will burn out, and black holes will dominate the scenery, slowly evaporating, particle by particle, in the cold abyss. This far future is not grim, but profound. It is not the absence of purpose, but the ultimate expression of transformation. The cosmos, from its birth in a flash of light to its slow fade into entropy, is an unfolding of possibility. That it gave rise to galaxies, to stars, to life, and to minds that ask these questions is a reflection not just of physical law, but of contingency, emergence, and wonder. And, even here, among collapsing globes of gas and retreating horizons, new questions bloom. Could there be other universes beyond our own observable edge? Might the inflation that seeded our cosmos have birthed others, each with their own laws, their own physics, their own time? The multiverse, once a speculative idea, is now a serious proposition in cosmological circles. Some theories suggest that universes bubble into being like foam, each expanding into its own pocket of space-time. Others propose cycles, cosmic rebirths through black holes, bounces, or emergent quantum geometries. In these models, our cosmos is not the only story, but a page in a larger anthology. We do not yet know if these ideas are testable, but they serve a vital role. They remind us that explanations always open into further questions, that knowledge is not an end, but a pathway. Perhaps that is the deepest lesson of the universe. Its immensity is not designed to dwarf us, but to awaken us, to consider galaxies not merely as objects, but as relationships between matter and light, between energy and curvature, between chaos and order, is to realize that the universe is not something apart from us. We are its outcome and its witness. From the spiral arms of our galaxy to the collapsing cores of protogalaxies, from the dust between the stars to the jets of quasar light that travel for eons, we are entangled in this structure, composed of its remnants and guided by its patterns. To know it is to recognize that the cosmos is not merely a place, but a process, and that we, fleeting and fragile, are part of its unfolding. In that sense, the sky is not silent. It speaks through gravity, through photons, through the whisper of hydrogen and the flare of collapsing stars. All we need is to learn to listen.
In the early dawn of knowledge, when philosophers still walked barefoot across the stone courtyards of Athens, the ideas of space and time were anything but obvious to Aristotle. Space was something filled with objects, with motion, with what the eye could see. Time, by contrast, was abstract. No one could see time itself, only feel it pass. It was a measure of change, but by what standard, and against what frame, remained elusive. Motion, for Aristotle, was not the consequence of force. As we later came to believe, it was an expression of change from potential to actuality. An object fell because it desired to return to its natural place, and that place was at the center of the universe. It was not law, but intuition, a way of understanding the world through philosophical reasoning rather than measurement. And thus, he reasoned, a heavier object would fall faster than a lighter one, for it bore more of its intrinsic nature. But every line of reasoning is born from the age that gives it breath. Before clocks, before telescopes, before the very idea of speed as we now understand it, how could one measure acceleration? How could one distinguish constant motion from changing motion in that world? The idea that motion required a sustaining force made sense. A flying arrow, they believed, continued forward because the air behind it pushed it onward, a primitive notion of cause. From that, the logical conclusion followed: if nothing resisted motion, an object would move infinitely fast. This meant that a vacuum could not exist, for if there were empty space, then instant motion would follow. And if instantaneous motion existed, the world would unravel into absurdity. No force is infinite, therefore no motion should be. Space, then, must always be filled with something: air, water, fire, or a subtle, invisible substance, what some would later call the ether. Still, in the faint cracks of ancient knowledge, another idea was beginning to bloom, one not from Aristotle, but from less celebrated thinkers like Democritus, Epicurus, and later, Lucretius. They imagined a world made of indivisible particles, atoms moving through infinite emptiness. It was a vision too bold for its time. How could nothingness exist? How could there be a place devoid of anything, yet still be real? Aristotle rejected such a notion, not only because it contradicted his philosophical intuition, but because it lacked an explanation for motion. Why did these atoms move at all? What set them in motion? The atomists replied, the universe has always been in motion. But that was not enough for Aristotle, who believed knowledge must seek causes, not merely describe appearances. The world kept turning, and time marched on, in the hush of the Middle Ages. Small sparks began to glow in distant monasteries. Scholars like Philoponus, Hipparchus, and later, Roger Bacon and Robert Grosseteste began to question Aristotle. They experimented, measured, charted. They sought to unite the senses with numbers, intuition with proof. Through rough experimentation, they discovered that when two objects, one heavy, one light, were dropped, they fell at the same rate. This defied Aristotle's teachings, but matched what they observed. Slowly, they realized that what changed an object's motion wasn't its essence, but something external, of force. A new concept emerged: momentum. What we now call inertia. An object, once in motion, would continue moving unless acted upon. This marked a fundamental shift from believing that motion required continuous force to understanding that force caused change in motion. not motion itself. At that same time, a man named Leonardo da Vinci sat sketching observations of pendulums, flowing water, and falling objects. He lacked precision instruments but possessed something even more valuable, the eye of a careful observer. He began to notice that objects not only fall, they accelerate. From Leonardo to Galileo was a short step in time, but a long leap in thought. Galileo did not just observe. He measured. He experimented. Using inclined planes to slow falling objects, he measured intervals by the beat of his own pulse. And from this, he discovered that all objects in freefall accelerate at the same rate regardless of mass. A simple realization, but one that shattered thousands of years of Aristotelian thinking. Galileo also laid the foundation for measuring time, something no one before had truly done. He invented the pendulum clock, tuned the length of the cord to match regular intervals, and opened a door for physics, the door of law. But Galileo could not yet explain what kept planets circling the sun. He believed they moved in perfect circles because it was their nature, an echo of Aristotle still lingering. He overlooked or dismissed Kepler, who had already shown that planetary orbits were not circles, but ellipses. It was an omission, yet also a reminder no one reaches the truth alone. Science advances by relay, not by solitude. Meanwhile, in France, René Descartes was contemplating existence in space. He believed only one thing was certain, I think. Therefore I am. From that premise, he imagined a mechanical universe, a cosmos without emptiness like Aristotle. He believed that a vacuum was absurd. There could be no place where nothing existed. Every space must be filled. Every motion must result from contact. Every force must be a push or pull, not an action at a distance. He imagined the planets caught in invisible vortices, swirling cosmic whirlpools like pebbles carried in water. He could not accept that gravity might act without contact. That idea, he believed, defied reason. But that would later become the very thing he would confront in Newton. Christian Huygens, the Dutch physicist, continued the work of Galileo and Descartes. He calculated that objects in circular motion experienced inward acceleration, A equals v squared over r. He understood that circular motion was not natural, but required a force, the centripetal force, to keep an object from flying off. There was nothing remarkable about the apple itself. It fell, as all things fall. But to Newton, watching from the quiet of the orchard, the falling apple whispered of something deeper, a force that not only drew fruit to the ground, but might also hold the moon in its path. He began to wonder, what if the same invisible pull that brings objects downward also governs the dance of the planets? The thought was radical. Gravity, as Newton envisioned it, was not a push, not a vortex, not a mechanical shove from ether or air. It was a pull across emptiness, silent, instantaneous, reaching through the void. He did not explain how this force acted at a distance, only that it did, and in that silence, the world changed. With the publication of his Philosophia Naturalis Principia Mathematica, Newton laid out laws that would govern motion for centuries. His first law, an object in motion stays in motion unless acted upon. His second force equals mass times acceleration. and his third for every action. An equal and opposite reaction. 3 lines that would become pillars of a new physics. 3 sentences that rewrote the language of nature. But it was his law of universal gravitation that unraveled the heavens. The same force that made the apple fall held the moon in orbit. The planets, too, obeyed this rule, drawn toward the sun, yet never falling into it, always curving, always missing, always returning. Gravity was not a local curiosity, but a universal principle. No longer was the cosmos a place of separate spheres. Earth and sky were one continuum, bound by the same invisible hand. It was a triumph of unity. For the first time, the motions of stars and stones could be explained by a single idea. The universe became knowable, predictable, and for a moment, almost tame. Yet Newton's world was not without mystery. In his formulation, gravity acted across empty space. But what carried this force? What medium connected 2 masses if nothing lay between them? He offered no mechanism, only mathematics. To some, that was enough. To others, it was a wound in reason. Action at a distance remained a phantom real in calculation, unfathomable in substance. Still, the predictive power of Newton's laws silenced most objections. Comets that once seemed like divine messengers now followed curves that could be charted. Tides, once the domain of myth, could be forecast by the moon's position. The universe, once veiled in mystery, now yielded its rhythms to calculation. But as Newton's vision took hold, something subtler began to shift. The universe was no longer a stage for gods and souls, but a machine, a vast, clockwork mechanism wound at the beginning of time and ticking ever forward. In Newton's own words, God was necessary to set the system in motion, but once running, the laws required no further intervention. This idea spread quickly. Theologians resisted. Poets lamented. But the age of reason embraced it. The world became geometry, the sky, a set of equations, motion, mere arithmetic of matter. The cosmos seemed infinite, eternal, precise and disturbingly cold. Within this mechanical view, time became absolute. It ticked forward independently of events, like the regular beat of a perfect clock. Space, too, was fixed, a container in which objects moved. There was no curvature, no relativity, no distortion. Just a blank stage upon which forces played. This model brought incredible success. Engineers, astronomers, and navigators thrived under its certainty. Yet in that certainty, some began to feel something had been lost. The cosmos, once alive with intention, became mute. There was no why, only how. No meaning, only motion. Philosophy receded as equations advanced, and yet, not everyone accepted this silence. In the salons of Europe, in the monasteries of Italy, in the halls of Königsberg and Geneva, thinkers began to ask whether the universe was truly so rigid. If time was absolute, how could it be felt so differently? If space was fixed, why did perception twist its shapes? If nature was machine, where was the human soul? These questions waited. For though Newton's universe explained much, It could not explain everything. Light, for instance, refused to obey the tidy rules of matter. It bent, it interfered, it defied understanding. And gravity, still mysterious, remained instantaneous, a troubling fact for those who believed in finite cause and effect. Across Europe, curiosity grew restless. The certainty of Newton had been a comfort, but comfort breeds questions. If the universe was indeed a clock, then who had wound it? And why did some of its gears seem to stutter strange gears, like magnetism, light, or heat, that refused to click into the mechanical pattern? The nature of light became a riddle that unsettled even the most confident minds. Was it made of particles, as Newton himself believed, or was it a wave, like sound passing through air? Some experiments showed it bending around corners, interfering with itself like ripples on a pond. Others revealed that light could strike metal and knock loose tiny sparks, as if it were a bullet, not a wave. It behaved like both, and neither. It obeyed no single metaphor. And what of heat, that invisible fire which made metal expand and skin burn? Some called it a fluid, a substance named caloric that flowed from hot to cold. But this invisible substance could not be seen, trapped, or weighed. Others suggested that heat came from motion, the jostling of particles too small to see. If this was true, then everything solid and still was in fact dancing, trembling, alive beneath the surface. This view brought atoms back from philosophical exile. The ancient idea of tiny, indivisible particles, once dismissed as metaphysical fancy, now gained foothold in chemistry and physics alike. Invisible though they were, atoms explained much how substances combined, why gases expanded, why heat moved. The idea of a hidden world, a world of ceaseless, chaotic motion returned. Yet this invisible world raised strange dilemmas. If matter was made of atoms, what held them together? Why did some cling while others broke apart? And if everything moved endlessly, if time itself was stitched from motion, then what was motion through time? Could time change? Slow, bend? Not yet. Not in Newton's world. In his system, time flowed uniformly, unaffected by the observer, but a few daring thinkers began to see cracks. One of them was a patent clerk in Bern, a man who thought deeply about what it meant to move, to measure, to observe. Albert Einstein, with quiet precision, dismantled the foundation beneath absolute time. He asked a simple question: what if the speed of light was always the same? No matter how fast you moved, the answer was not so simple. If light never changed speed, then time must, and space must. The very fabric of the universe had to stretch, warp, and shift, depending on how one moved through it. With that, Newton's absolute space and time were undone. The universe was no longer a fixed grid. It was a woven cloth space and time stitched together, flexible, responsive, alive. Motion bent time. Gravity bent space. Mass became a measure of energy. Energy became fluid, shimmering, radiant. And gravity, that silent, unexplained pull, was no longer a force at all. It was a curve. Objects followed paths not because they were pulled, but because space itself was curved by mass. Planets orbited stars, not like marbles tugged by strings, but like dancers following the bend in a floor they could not see. It was a new language for an old story. Newton's apple still fell, but now it fell not because it was pulled, but because Earth had curved the stage beneath it. And light, too, bowed its head to gravity, bending its path near stars, revealing that even something thought massless could be swayed by the shape of space. Einstein had not replaced Newton, he had deepened him. Just as Newton once made Aristotle a special case of a larger truth, so Einstein made Newton's laws a shadow of a deeper structure, visible only at great speeds or near great masses. The clockwork cosmos had become a living geometry. Yet this geometry introduced its own enigmas. If space and time were relative, then what anchored reality? If the universe could bend, then could it twist into loops? Could time itself fold, allowing effects to precede causes? And if energy and matter were interchangeable, then what truly was substance? More unsettling still was what the new physics implied about the origin of the cosmos. If space could expand, then perhaps it had once been smaller, much smaller. Perhaps everything time, matter, energy had once been compressed into a single point, a beginning not just of things, but of being itself. The questions multiplied, the answers dissolved. Where Newton had drawn clean lines, Einstein sketched curves. Where Descartes saw machinery, Einstein saw elegance. The universe had not become less comprehensible, but it had become more mysterious. And mystery, once again, became the beginning of knowledge. The universe was no longer content to be seen. It now had to be imagined. In the dark silence between stars, space itself was growing, stretching not into something, but into itself. Galaxies receded, not because they moved through space, but because the very fabric of space was expanding between them. It was not an explosion through a medium, but a swelling of the medium itself, silent, unceasing, without center. What had once seemed eternal now had a beginning, a birth not from chaos, but from a singularity, a point of infinite density, infinite temperature, infinite curvature, a place where the known laws of physics broke apart. The so-called Big Bang was not an outward blast from a location, but a beginning of space and time alike. There was no before. There was no outside. The cosmos began not within something, but as something. And yet, what emerged from that singularity was not chaos, but order astonishing, fragile order. Forces separated, symmetries broke, particles formed. The blueprint of all that would ever exist was imprinted in those first moments. A fraction of a second after it began, the universe knew how to build stars, how to shape galaxies, how to breathe atoms into being. But this precision was unnerving. Why should the laws be so finely tuned? Why did gravity have just the right strength to allow galaxies, but not too strong to crush everything into black holes? Why was the expansion rate so delicately balanced that it did not halt or tear itself apart? Why were the constants of nature so exact, as if written with intent? Some saw providence. Others saw coincidence. Still others imagined multitudes a multiverse, infinite in variety, in which every possible configuration existed somewhere in that vast landscape. Our universe might not be special. It might simply be one of the few in which life could ask the question. But questions multiply in dark rooms. If space could expand, could it also tear? Could it form holes not just in space, but in the very order of cause and effect? General relativity permitted such structures, black holes, regions from which nothing, not even light, could escape. Not because something was pulling inward, but because the inward became all there was, the future, for anything crossing that boundary, pointed only deeper within, and what lay inside, no one knew. The equations collapsed, space folded into space, time folded into time. Mass became infinite, a singularity. Again, not at the beginning, but at the heart of unbeing. These were no longer philosophical riddles. They had become observable realities. Black holes were not just the fate of collapsed stars. They were real, detectable by their hunger, their shadows, their ripples in space-time. Einstein had not predicted them with joy, but with reluctance. He doubted they could form the universe. He hoped would not allow such monstrosities. But the universe allowed, and not just permitted, it required. Black holes formed not rarely, but often. They anchored galaxies. They shaped structure. They sculpted the cosmos like unseen hands, where Newton had given us force, and Einstein had given us curvature. Black holes gave us boundaries not physical, but conceptual. Inside their event horizons, all knowledge ended. No observer could report from within. No signal could return. In an age where physics had pried open the heavens, black holes were doors that remained shut, yet even they were not eternal. As Stephen Hawking later showed, black holes could radiate slowly, imperceptibly. They could evaporate. Through a quantum whisper at their edge, information could bleed away. And with it came a final paradox. If black holes destroyed information, then the laws of physics, which demanded reversibility, would fail. A tear appeared between the smooth curves of general relativity and the jittering probabilities of quantum mechanics. They were both true, and yet together, incomplete. The universe at large obeyed one rhythm. The universe of the small danced to another. Between them lay a silence no theory could cross. In that silence, some imagined strings vibrating filaments, infinitesimal, whose modes of vibration gave rise to mass, charge, force. Others imagined loops, granular time, or emergent space. But none could yet bridge the gap. The quest for a theory of everything had become the quest for a language the universe was still unwilling to speak. In the search for unity, the questions had only deepened. The more the universe revealed, the more elusive its heart became. What began as a desire to understand motion had led to a trembling awareness of mystery, not for lack of knowledge, but because knowledge had reached its edge. It was not just the cosmos that grew strange, but consciousness itself. If space could curve and time could stretch, Then what of the observer in quantum theory? The act of observation changed the outcome. Particles existed in clouds of possibility until measured, as though reality itself required a witness. The boundary between world and mind blurred. Was consciousness merely an emergent function of matter? Or was it somehow woven into the very fabric of being? Some thought of the ancient Pythagoreans, who had believed that number and harmony governed all things. Others recalled the mystics, who spoke of the illusion of separateness, the unity behind form. Modern physics, in its own way, had circled back to such riddles, not in doctrine, but in implication. The vacuum, once dismissed by Aristotle as absurd, now seethed with energy a sea of fluctuations, particles appearing and vanishing in ghostly pairs. Emptiness was no longer empty, even nothing. It seemed, was something, and the universe itself, it still expands, accelerating with an energy no one can name. Dark energy. They call it not because it is understood, but because it is not. It pushes galaxies apart with a silent force, shaping the fate of everything, yet remaining beyond reach. Dark matter, too, passes unnoticed through all we see. It outweighs the visible stars, yet never shines. It holds galaxies together like scaffolding made of shadows. It neither emits nor absorbs light, but its gravity carves the shape of the cosmos. The familiar now floats in a sea of the unknown. All that we call atoms, stars, and light is but a sliver, a small island of the comprehensible amid a vast ocean of the hidden, and time, that old companion, may not be eternal. Some theories speak of a heat death, a future in which stars burn out, black holes fade, and all gradients dissolve. A universe of uniformity, cold and still, where nothing more can happen. Others imagine cycles, rebirths, bouncing cosmologies, where the end curls into a beginning. But even if the cosmos fades, the questions remain. Why do laws exist at all? Why should anything be ordered, measurable, or beautiful? Why is there something rather than nothing? No equation has answered that. No telescope has glimpsed its edge. We ask not because we are ignorant, but because we are aware. We seek not merely to explain, but to belong. The universe, in its vastness, does not speak, but it allows us to listen. From Aristotle's unmoved mover to Newton's universal law, from Einstein's curvature to the quantum veil, each step has drawn us deeper, not into certainty, but into awe. Perhaps the ultimate lesson is not how the universe works, but that we can ask at all. That in a corner of space, for a brief span of time, there are minds capable of wonder, and wonder, like gravity, pulls us forward.
What if we could look back in time, not just decades or centuries, but billions of years? What if we could see the first stars ignite, the first galaxies swirl into form, the first light pierce through the primeval dark? What would we find in the universe's ancient dawn? Would it confirm everything we believe we know, or force us to rewrite the very laws of cosmic evolution? High above Earth, beyond the blue sky and above the clouds, a machine was sent on this very quest. A journey not of distance, but of time. It began its ascent silently rising through the thick atmosphere into the boundless night, bound for a destination unlike any other, 15 million kilometers from Earth, at a place where the gravity of the Sun and Earth perfectly cancel out. It came to rest, suspended in celestial equilibrium at the second Lagrange point. This was no ordinary observatory. It was a gateway to the deep past. There, in the cold vacuum of space, the James Webb Space Telescope slowly unfolded, like an origami flower blooming in zero gravity. Golden hexagonal mirrors clicked into alignment. Delicate sunshields stretched out like wings to block the harsh solar glare. And the observatory cooled, waiting, listening, watching. After decades of design and $10 billion of international collaboration, it was time a signal from Earth awakened the telescope's instruments, and at last, after years of anticipation, Webb opened its golden eye and began to see. What it saw changed everything. JWST, with its infrared gaze, was built to do many things: peer into stellar nurseries, study alien worlds for signs of life, and trace the faint afterglow of cosmic birth. But its most astonishing revelations came when it turned its attention to the very beginning, the first billion years after the Big Bang. Astronomers had long predicted what the early universe should look like, according to the Standard Model, our cherished lambda cold dark matter framework. The cosmos began small and simple. Galaxies were supposed to emerge slowly, assembling through countless mergers of smaller structures. They should have been faint, irregular, and primitive. But JWST revealed something startling. In the haze of ancient light, it found fully formed galaxies, large, luminous, structured, far too massive, far too early. They stood like ancient cities in the wilderness, monuments built in cosmic time, too short for such architecture. According to our best theories, they shouldn't even exist. For some, this was a call to update our models of star formation and early cosmic evolution. For others, it was far more unsettling, a crack, perhaps, in the foundations of modern cosmology. Could it be that dark matter behaves differently than we thought? Could dark energy, or even the fabric of space-time itself, be changing in ways we have yet to understand? This would not be the first time the universe has surprised us. From Galileo's first glimpse of Jupiter's moons to Hubble's discovery of an expanding universe, every new instrument has rewritten a chapter in our cosmic story. And now, with the James Webb Space Telescope casting its eye further into the past than anything before, we are once again at the threshold of discovery. So, what do these ancient galaxies truly tell us? Are they anomalies? Outliers to be explained? Or are they messengers from a deeper, more complex truth? This is the story of the universe's first great structures, the story of the galaxies that weren't supposed to be there, and the story of a telescope that may just change everything we thought we knew about the beginning of time. Eyes to the heavens. To gaze upward is to engage in an ancient ritual, a tradition as old as our own intellect, but the transformation of that gaze into a disciplined exploration began in earnest 4 centuries ago, when Galileo Galilei first pointed a telescope toward the night sky. Though the telescope had only recently been invented, primarily as a tool for earthly pursuits such as navigation and warfare, Galileo redirected its purpose toward the heavens. In doing so, he planted the seeds of a scientific revolution. With nothing more than a simple configuration of lenses, he observed the phases of Venus, the moons of Jupiter, and the pockmarked surface of the Moon, shattering the long-held notion of celestial perfection. A few decades later, Isaac Newton took the next logical leap. By replacing lenses with a curved mirror, Newton eliminated the chromatic aberrations that plagued refracting telescopes and created the prototype for the modern reflector, laying the foundation for today's colossal observatories, including the James Webb Space Telescope. Newton's mechanical insights into optics may not have directly transformed astronomy, but his universal laws of motion and gravitation reshaped our understanding of celestial mechanics. The orbits of planets, moons, and comets were no longer seen as divine choreography, but as the natural consequence of mathematical laws, elegant, immutable, and pervasive. As telescope technology improved, so too did our ability to collect and refine the light of the cosmos. With each refinement, longer focal lengths, larger apertures, better mirror coatings, the universe revealed more of its grandeur, more of its complexity. By the mid-18th century, French astronomer Charles Messier was among those using telescopes to hunt for comets drawn to their glowing comas produced by the sublimation of ice and dust as they neared the sun. But Messier's work was repeatedly interrupted by fuzzy, unmoving smudges in the sky that did not behave like comets at all. These interlopers didn't move night to night. They refused to perform as expected. To avoid wasting time, Messier began cataloging them, curating a list of distractions, most of which turned out to be nebulae or star clusters within our own galaxy. Yet, unbeknownst to Messier, some of these faint objects were far more distant, entire galaxies in their own right. Through the 19th century, telescopic enhancements revealed structure in some of these enigmatic smudges, spiraling arm symmetry rotation, suggesting they were more than gas clouds. These visual cues led to a growing debate: were these spiral nebulae part of our own Milky Way? Or were they island universes, external galaxies far beyond our stellar neighborhood? This central question culminated in the Great Debate of 1920 between Harlow Shapley, who believed the Milky Way was the entire universe, and Heber Curtis, who argued for a far more expansive cosmos populated by myriad galaxies. It was Edwin Hubble who ultimately settled the matter, using the 25-meter Hooker telescope at Mount Wilson Observatory. Hubble resolved individual stars in the Andromeda Nebula and determined its distance via Cepheid variable stars. The results were staggering. Andromeda lay well beyond the Milky Way. Not only was our galaxy not alone, but the universe was vastly larger than previously imagined. And more still, Hubble discovered that nearly all galaxies are receding from us, their light stretched into longer, redder wavelengths by cosmic expansion. In a few short years, the universe had gone from a static stage to a dynamic, evolving entity, a cosmos that was born in a fiery beginning we now call the Big Bang. This monumental realization sparked new questions. If the early universe was hot, dense, and nearly uniform, where did the vast structures we see today originate? What mechanisms sculpted galaxies from that primordial smoothness? As telescopes continued to grow throughout the 20th century, both in aperture and technological sophistication, astronomers pursued these questions deeper into the dark. Earth-based observatories pushed the envelope with mirror diameters reaching 10 meters, allowing them to pierce through layers of dust and reach fainter, more distant light. But they were ultimately limited by Earth's own atmosphere, whose constant turbulence blurred incoming starlight. The solution was to escape the atmosphere entirely. In 1990, the Hubble Space Telescope was launched into low Earth orbit, carrying a modest 25-meter mirror but free from atmospheric distortion. The clarity of its images transformed both science and public imagination, producing iconic photographs of galaxies, nebulae, and deep cosmic vistas that adorned both academic journals and classroom posters around the world. But science does not rest on its achievements. Even before Hubble had reached full operation, plans were underway for its successor, a telescope that would peer not merely into distant galaxies but into cosmic history itself. The James Webb Space Telescope. A marvel of modern engineering was envisioned to carry a 65-meter segmented mirror, far too large to fit into a rocket in one piece. Like some vast piece of origami, the telescope would have to be folded for launch and delicately unfurled in space. Its destination was not Earth orbit, but a gravitational perch, 15 million kilometers away the Sun, Earth Lagrange point L2. There, in the frigid silence of deep space, it would be shielded from the sun's heat by a 5-layer sunshield the size of a tennis court, cooled until it could detect the faint infrared glow of the earliest galaxies. After decades of delays, cost overruns, and technological challenges, JWST launched on Christmas Day 2021, riding atop an Ariane 5 rocket and carrying with it the hopes of an entire generation of astronomers. Its mission to chart the life cycles of stars, to study the atmospheres of distant exoplanets for signs of life, and most ambitiously to search for the first galaxies ever formed to witness the dawn of structure in the universe. What it would find no one could say for sure, but one question loomed large. Where did galaxies come from, and when did they arise in the cosmic timeline? The answer lay in light that had traveled for over 13 billion years, emitted by stars and galaxies that lived and died long before Earth even formed. As James Webb opened its golden eye to the deep sky, it began collecting this ancient light, offering us not just a glimpse, but a new window into the formative epochs of the cosmos, one capable of changing everything we thought we knew. The first galaxies. To understand the first galaxies, we must embark on a journey not merely through space, but through time, reaching back across the eons to a cosmos still unformed, still raw with potential. The tale of these primordial structures begins with a paradoxical fusion, a story that connects the largest scales of the universe to its smallest weaving together, the tapestry of galaxies from quantum ripples in space-time itself. Our modern tools for exploring this tale are many, but one of the most transformative is the Planck satellite launched in 2009, and for a time, the coldest known object in space. Its mission was not to observe stars nor even galaxies. Instead, Planck mapped the entire sky in exquisite detail, focusing on the cosmic microwave background, the afterglow of the Big Bang. This radiation is ancient, stretching across the universe at a uniform temperature of roughly 273 degrees above absolute zero. But within that uniformity lies the key to cosmic structure: tiny temperature fluctuations, 1 part in 100,000, representing the earliest imprints of gravitational variation. These ripples were not random. They originated from quantum fluctuations during an extraordinary event known as cosmic inflation, which occurred just a fraction of a second after the Big Bang. Inflation magnified microscopic fluctuations to macroscopic scales, imprinting space itself with density variations. When inflation ended, these frozen quantum disturbances were filled with energy, becoming the seeds of galaxies yet to form. As the universe cooled, particles condensed. Within the first microsecond, quarks were locked into protons and neutrons. After a few minutes, these fused into the first atomic nuclei. They're mostly hydrogen and helium. The fires of primordial nucleosynthesis burned briefly but profoundly, leaving behind a smooth sea of atomic matter, now expanding and cooling through time. Yet for nearly 100 million years, the cosmos lay in darkness, a period aptly named the Cosmic Dark Ages. Though matter existed, no stars had yet formed to light the skies. Still, gravity worked silently, shaping structure through the invisible scaffolding of dark matter. Unlike ordinary matter, dark matter does not interact via light, but its gravitational pull is immense. It began to collapse into overdensities, regions where matter was slightly denser than average. These overdensities grew and merged, forming the first dark matter halos, gravitational wells into which ordinary matter would later fall. Ordinary matter hydrogen and helium gas responded differently. It could cool, compress, and radiate energy, unlike its dark counterpart. Eventually, as gas settled into these halos, it began to fragment. The densest fragments collapsed under their own weight, and in their cores temperatures rose high enough for nuclear fusion to ignite. Thus, after a cosmic slumber, the first stars flared into being. These stars, known as population 3 stars, were fundamentally different from the stars of today. They contained only hydrogen and helium, lacking the heavier elements, what astronomers call metals, that are forged in stellar interiors. Without these metals to aid cooling, these early stars grew to tremendous sizes, often exceeding 100 times the mass of our Sun. They burned hot and bright, emitting intense ultraviolet radiation, but their lives were brief, just a few million years before ending in dramatic supernova explosions or collapsing directly into black holes. With the birth of these first stars came the epoch of reionization. Their powerful radiation ionized the surrounding neutral hydrogen, stripping electrons from atoms and transforming the universe's dark plasma into a transparent, glowing cosmos. This transition, marked by growing bubbles of ionized gas, signaled a universe awakening. Yet the story of the first galaxies had only just begun. Stars do not form in isolation. They cluster their gravitational attraction, drawing them into associations. The early universe seeded with these dark matter halos, and increasingly enriched with metals from supernovae, began to assemble the first protogalaxies. But defining a first galaxy is not straightforward. Unlike stars, which ignite in a discrete event, galaxies evolve gradually. They grow through accretion, the slow gathering of gas, and through mergers where smaller systems collide and combine into larger ones. What we observe today as majestic spirals and giant ellipticals began as modest knots of matter coalescing under the persistent influence of gravity. These formative galaxies were not all successful. In the smallest halos, a single population 3 star could disrupt the entire system. Its supernova might expel all remaining gas, halting further star formation, and leaving behind a dark halo, what we call a dark galaxy. Such ghostly remnants may still drift unnoticed through the cosmos. However, in larger halos, gravity prevailed, gas was reaccreted, and successive generations of stars began to form. These newer stars, now enriched with trace amounts of carbon, oxygen, and heavier elements, were markedly different from their predecessors. The presence of metals altered the opacity of stellar material, affecting how energy moved through the star and changing its evolution. Stars, like our Sun, with lifespans of billions of years, became possible. Thus began the transition from the first galaxies to the galactic zoo we observe today. The most massive halos continued to grow, attracting and merging with others. This hierarchical buildup is a cornerstone of the LCDM model, our best current theory for the structure of the universe. But not all galaxies grew at the same rate. Some remained small, fragile collections of stars, while others ballooned into giants. As mass increased, so did stability. Larger galaxies retained their gas even after supernova, supporting sustained star formation across cosmic time. These galaxies became cosmic engines, generating light metals and structure on ever larger scales. Meanwhile, as stars aged and died, the heavy elements they produced were dispersed, enriching the interstellar medium. This chemical evolution is crucial. Without carbon and oxygen, there would be no Earth, no life, and no astronomers to tell this story. What began as imperceptible quantum ripples now echoed across billions of light years. The cosmic microwave background, once uniform, had evolved into a universe populated with galaxies. each a complex ecosystem of gas stars, black holes, and dark matter. And though we can simulate much of this history with remarkable precision, observations always bring surprises. The James Webb Space Telescope, our most powerful observatory to date, has begun to peer into this epoch. Already, it has challenged expectations, revealing galaxies more massive, more structured, and more numerous in the first billion years than theory had predicted. These findings do not undermine our cosmological framework, but instead sharpen it. As in all science, anomalies are invitations, prompts to revisit assumptions, refine models, and look deeper. The early universe is a frontier not only of time and distance, but of knowledge. We stand now at its edge, our instruments pointed skyward, seeking in the ancient light the answers to questions formed by the fusion of curiosity and reason. The first galaxies were not monumental in size nor grand in appearance, but they were monuments of process evidence that gravity, chemistry, and time, guided by the laws of physics, could sculpt the void into luminous form. From the tiny ripples imprinted in the quantum fog of the early universe to the brilliant spirals now wheeling across our skies. This is the journey of structure, of complexity, and ultimately of us. For somewhere in one of those fledgling galaxies, a sun would one day rise, and orbiting that sun, a small rocky world would look back at the stars and wonder how it all began. The Galactic Zoo. In 1932, amidst the dawn of global radio communications, a peculiar discovery emerged not from the optical lens of a telescope, but from the static of a radio receiver. Carl Jansky, an engineer at Bell Telephone Laboratories, was investigating sources of interference in transatlantic radio signals when he noticed something strange, a persistent hiss of background noise, faint but measurable. Initially, he attributed it to terrestrial causes, perhaps lightning or electrical equipment. But the mystery deepened when Jansky observed that this static did not align with the rhythm of Earth's 24-hour solar day. Instead, it shifted ever so slightly, adhering to a cycle just under 24 hours. Sidereal time, the time taken for distant stars to return to the same position in the sky. This seemingly minor discrepancy of 4 minutes per day carried profound implications. It meant that the source of this radio interference was not of earthly origin, nor even tied to the sun, but came from well beyond our solar system. Jansky had inadvertently detected radio waves from the Milky Way itself, the first ever confirmed reception of electromagnetic radiation from deep space outside the visible spectrum. This serendipitous moment marked the birth of radio astronomy. Although Jansky himself was redirected to other duties and did not pursue the discovery further, his name became immortalized in the field. Today, we measure the strength of radio emissions from celestial sources in Jansky's. Others picked up the mantle. Notably, Grota Reber, a young engineer and amateur radio enthusiast, constructed the world's first purpose-built radio telescope in his backyard. For a time, he was the only practicing radio astronomer on Earth. Through his work, Reber confirmed Jansky's findings and revealed that the Milky Way emitted radio waves across the sky, opening a new window onto the cosmos. Soon as radio telescopes proliferated and improved, astronomers discovered more than just emissions from our own galaxy. They detected incredibly powerful radio sources, compact, bright, and seemingly point-like, that emitted energy on a scale difficult to reconcile with known stellar processes. These mysterious objects came to be known as quasi-stellar radio sources, or quasars. Appearing star-like in optical images but blazing with radio energy, quasars were later understood to be powered by supermassive black holes, some with masses exceeding 1 billion suns, feeding on surrounding matter and releasing enormous amounts of energy as they accreted gas and dust. These beacons could be seen across billions of light years, revealing not only their own immense power, but also illuminating the early universe itself. Quasars represented just one expression of the intense activity that characterized the first few billion years of cosmic history. During this primordial epoch, the universe blazed with light and change. First stars ignited, first galaxies assembled, and first black holes fed ravenously. But as the universe aged, the youthful fervor of cosmic activity waned. Star formation began to slow, and galaxies matured into more stable configurations. Yet even in this apparent calm, gravity continued its work, relentlessly driving evolution on every scale. Galaxies, like living organisms, changed with time. Small galaxies merged and coalesced into larger ones. Larger galaxies in turn consumed their surroundings and grew more massive still. Some galaxies developed distinct structures shaped by their internal dynamics. Disk-shaped galaxies like our Milky Way spun into elegant spirals, their rotation sustained by the conservation of angular momentum. Cold gas within these spinning disks collapsed into stars, forming the grand design spirals that populate astronomical catalogs today. Other galaxies suffered more turbulent fates. Violent mergers between massive galaxies often disrupted their ordered rotation, transforming them into chaotic amorphous systems known as elliptical galaxies. Lacking the structured spiral arms of their cousins, these spheroidal galaxies contain older stellar populations and less gas, signaling the end of vigorous star formation. The cosmos thus revealed a dichotomy in galactic morphology spirals and ellipticals, each reflecting distinct evolutionary pathways shaped by collisions and environmental interactions. Yet not all galaxies fit these tidy classifications. Some appear misshapen or irregular, likely distorted by gravitational interactions, past mergers, or ongoing encounters with neighboring systems. These irregular galaxies serve as transitional objects, snapshots of galaxies caught mid-transformation still bearing the scars of their recent histories. In the observable universe, astronomers estimate the existence of up to 1 trillion galaxies, varying wildly in scale. Most are modest, containing a few billion stars, but a select few are true giants hosting hundreds of billions or even trillions of stars. These galaxies are not scattered randomly. Rather, they trace a vast interconnected structure of matter known as the cosmic web, a lattice of filaments and nodes shaped by the primordial fluctuations seeded during inflation and sculpted by dark matter over cosmic time. In this web, vast voids regions nearly devoid of galaxies span millions of light years, while matter flows along filaments and sheets toward gravitational wells. These wells correspond to massive conglomerates of galaxies and dark matter. Galaxy clusters. Clusters are gravitational fortresses housing hundreds or thousands of galaxies swimming in a hot plasma called the intracluster medium, all immersed in massive dark matter halos. At the heart of the largest clusters reside the titans of the galactic realm, CD galaxies, monstrous ellipticals that dominate their environment and continue to grow through cannibalism and accretion. Clusters themselves form larger structures, superclusters which span hundreds of millions of light years. Our own Milky Way is part of one such structure, the Laniakea supercluster encompassing millions of galaxies. Whether superclusters are gravitationally bound or merely transient associations remains an open question, but they mark the largest coherent features in the known universe. Not all galaxies live in clusters. In fact, most reside in smaller associations known as galaxy groups. These more intimate gatherings consist of a few to several dozen galaxies, typically anchored by 1 or 2 massive members. Our Milky Way is part of such a group. The local group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and over 100 dwarf galaxies. Many of these faint companions have only recently been discovered through deep sky surveys enabled by modern telescopes. The local group, while unassuming compared to massive clusters, has become a laboratory for understanding galactic evolution. In particular, it has revealed a truth that reshapes our conception of galaxies as static finished entities. Galaxy evolution is not over. In fact, it is happening around us right now. A striking example of this ongoing process was discovered in the early 1990s by Rodrigo Ibada, a young graduate student at the University of Cambridge, working with the Anglo-Australian Telescope in New South Wales. Ibada was studying the dynamics of stars near the Milky Way's central bulge. His observations, conducted with the aid of optical fiber instruments capable of measuring the motion of dozens of stars, simultaneously uncovered something strange. Amid the random motions expected in the galactic bulge, a subset of stars appeared to be moving coherently, as if they shared a common origin. Ibata ruled out measurement errors and computational mistakes. The evidence grew harder to ignore. With the guidance of his supervisors, Jerry Gilmore and Mike Irwin, Ibata reached a bold conclusion. These stars were not native to the Milky Way. They belonged to a separate external system, an intruding dwarf galaxy. The discovery of the Sagittarius dwarf galaxy provided direct evidence that the Milky Way was in the process of consuming another galaxy. This satellite galaxy, stretched and distorted by our galaxy's gravity, was being torn apart, its stars scattered into tidal streams across the sky. What was once a coherent stellar system would eventually be subsumed into the Milky Way's halo, lost among its billions of stars. Since then, astronomers have found that Sagittarius is not alone. The Milky Way is consuming multiple dwarf galaxies, remnants of which are still detectable in the form of faint stellar streams. Andromeda, our galactic neighbor, is doing the same. Galactic cannibalism is not an occasional event. It is a central mechanism of galactic growth. The peaceful serenity we attribute to our night sky belies a violent and ongoing process of accretion and destruction. Thus, our understanding of the galactic zoo, the diversity of galaxies and their behaviors, has matured through decades of observation and theoretical work. We now comprehend galaxies not as isolated objects, but as products of environment history and ongoing interaction. They are born in the dense knots of dark matter, nurtured by gravity and gas, shaped by internal dynamics and transformed by cosmic encounters. They live, grow, and sometimes die, collapsing into black holes or being devoured by larger systems. Yet for all our knowledge, the universe continues to challenge us. As recently as 2022, new observations from the James Webb Space Telescope hinted that the earliest galaxies might be more massive and more developed than current models predict, stirring debates and forcing us to re-examine long-held assumptions. From the quantum ripples that ceded structure to the majestic spirals and monstrous clusters we observe today, the cosmos reveals itself as both an archive of ancient processes and an active dynamic entity. To map this evolution is to trace a vast and interwoven story, a narrative written in stars and dark matter and gas and radiation in the grand interplay of gravity and time. It is the story of everything we see in the night sky, and it is still being written. The James Webb Mystery. It began with a roar that echoed across the blue Christmas morning sky, a column of fire lifting humankind's most ambitious eye into the heavens. A telescope unlike any before. It folded like cosmic origami, was flung across the void to take position 1.5 million kilometers from Earth, far beyond the pull of our planet's gravity, to a place where the forces of Earth and Sun are balanced in celestial harmony. There, at the second Lagrange point, JWST unfurled its golden mirrors, cooled to the chill of deep space, and prepared to look far back toward the first flickers of starlight that ever pierced the darkness. As the James Webb Space Telescope opened its eye on the young universe, astronomers around the globe found themselves transfixed and then puzzled. What they saw in those first images from the primordial cosmos did not align with what decades of theory had led them to expect. There, shining from a time less than 1 billion years after the Big Bang, were galaxies that looked too big, too luminous, too structured. Some were beautiful, rotating disks, grand spirals eerily reminiscent of our own Milky Way. But how could this be? In a universe still in its infancy, how had such galaxies already matured? One paper, cheekily titled "Panic at the Disks," captured the sentiment cosmologists watched as headlines around the world began to declare an existential crisis had JWST disproven the very foundations of cosmology. Was the Big Bang model broken? Were the equations of the universe undone? To make sense of the excitement and the unease, we must journey into the very heart of modern cosmology and ask a simple but profound question: what kind of universe do we live in? The story begins, as so many great stories do, in the early 20th century. Albert Einstein, forging a new understanding of gravity, had just unveiled his general theory of relativity, a framework in which space and time were no longer passive stages, but active participants in the cosmic dance. Others followed in Einstein's wake: Friedman, Lemaitre, Robertson, Walker. Their solutions to Einstein's equations revealed a startling possibility: space itself was not static. The universe could stretch, evolve, and expand. And then came Edwin Hubble. In the 1920s, observing from Mount Wilson, he found that distant galaxies were redshifted. That is, their light was stretched as if fleeing from us. The more distant the galaxy, the greater the shift. The conclusion was inescapable. The universe was expanding. And if it was expanding now, it must have been smaller, denser, and hotter in the past. Thus was born the Big Bang theory, not an explosion in space, but an expansion of space itself from a seething, high-energy beginning. But relativity, elegant as it is, offers not one solution, but many. Mathematically, the equations can describe countless possible universes. To know which one we inhabit, astronomers needed data, specifically 2 crucial measurements: the current rate of expansion and the contents of the universe. The first of these is the Hubble constant, which tells us how fast galaxies recede as a function of their distance. The second concerns the energy budget of the cosmos, how much of it is made of matter radiation and other more exotic components. Measuring these values became the central task of observational cosmology for most of the 20th century. Determining the Hubble constant was notoriously difficult. The universe, unfortunately, does not provide measuring sticks. Estimating cosmic distances required creative methods using standard candles like Cepheid variables and Type Ia supernovae, whose intrinsic brightness is known to deduce their distance from apparent brightness. For decades, astronomers debated whether the Hubble constant was closer to 50 or 100 kilometers per second per megaparsec, a disagreement that translated into wildly different estimates of the universe's age. It was only in the 1990s, with the deployment of the Hubble Space Telescope, that clarity began to emerge. With unprecedented precision, HST measured the distance to nearby galaxies, settling on a value near 72 kilometers per second per megaparsec, implying a universe roughly 138 billion years old. Visible matter stars, planets' gas was easy enough to tally, but something strange lurked in the motions of galaxies and clusters. Spiral galaxies rotated too fast at their edges. Clusters of galaxies held together despite insufficient visible mass. The only explanation was that some unseen substance, dark matter, was exerting gravitational influence. Though invisible to light, its presence was undeniable. The universe, it seemed, was mostly made of things we could not see. And then came a revelation so startling, it won the Nobel Prize 2 teams. The Supernova Cosmology Project and the High-Z Supernova Search Team studied the light of exploding stars to chart the expansion history of the universe. Their expectation was clear. Gravity, acting over time, should slow the expansion. But the data told a different story. Instead of decelerating, the universe was accelerating, expanding faster and faster as time went on. What could be driving this cosmic acceleration? The answer, though speculative, lay in the mathematics of general relativity, a mysterious form of energy permeating all of space, exerting a repulsive pressure. It became known as dark energy, a force unlike any seen before, whose nature remains one of the deepest mysteries in physics. With these discoveries, cosmologists assembled a model of the universe now known as LCDM, lambda, cold, dark matter. Lambda stands for the cosmological constant, Einstein's term for dark energy. CDM refers to cold dark matter slow-moving and clumping, which seeds the formation of galaxies. According to LCDM, the universe is 138 billion years old, composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy. This model has passed countless observational tests. It predicts the pattern of cosmic microwave background radiation, the distribution of galaxies on large scales, and the evolution of cosmic structure. It is by all accounts an astounding triumph of science. The galaxies observed by JWST appeared not only earlier than expected, but brighter, more massive, and more structured than models had predicted. Some appeared to contain hundreds of billions of stars, less than a billion years after the Big Bang. In theory, such massive systems shouldn't have had enough time to form. Cosmological models like LCDM govern the evolution of the universe on the largest scales, how space expands, how matter clumps. But to predict the formation of galaxies, we must go further. We must simulate the flows of dark matter and gas, the cooling of plasma, the birth of stars, the feedback of supernovae and the ravenous hunger of black holes. This is astrophysics in full complexity, a dance of scales and forces that challenge even our most powerful computers. To cope, astronomers employ recipes' simplified rules embedded in simulations to approximate the messy physics of galaxy formation. These recipes are based on the best available data but often rely on assumptions. One of the most critical is the stellar initial mass function, a statistical description of the distribution of star masses formed in a given gas cloud. In the local universe, the IMF is relatively well constrained. But what if it was different in the early cosmos? If, for example, early star formation favored more massive luminous stars, then young galaxies would shine more brightly than expected, for their mass astronomers assuming a local IMF would overestimate their size and maturity. Such a skewed IMF could help explain why JWST's galaxies seemed anomalously bright. Perhaps they weren't so massive after all, just composed of hotter, more massive stars. Moreover, early results from JWST were based on rapid preliminary analyses. The telescope's instruments are extraordinarily sensitive, and interpreting their data requires meticulous calibration. Redshifts must be confirmed spectroscopically, not just estimated photometrically. Initial excitement often gives way to more sober reanalysis. And that is precisely what is happening. As JWST continues its observations and astronomers refine their models, the panic is subsiding. The LCDM framework remains intact. The early universe may be more complicated than expected, richer, more dynamic, but that is not a crisis. It is the fulfillment of JWST's mission. For telescopes do not exist to confirm what we already know. They are built to challenge our assumptions, to expand the boundaries of the known. Every deviation, every outlier, every unexpected galaxy is a clue, an invitation to look again, think deeper, and refine our understanding of the cosmos. What the James Webb Space Telescope is revealing is not the failure of cosmology, but its vitality. It reminds us that science is not a monument, but a process, a conversation with nature that unfolds over time. It is a testament to our curiosity, our creativity, and our willingness to question even our most cherished theories. In the end, the galaxies JWST glimpsed in the early cosmos are not harbingers of doom, but messengers of wonder. They whisper of a universe that came alive faster than we imagined, of stars that blazed into existence amid chaos, and of a cosmos still full of secrets waiting to be unveiled. And so the story continues, one observation at a time, one photon at a time, as we reach deeper into the darkness, searching not for certainty, but for understanding.